whatever that last day was. Tuesday, thank you. Okay, so the vacuum, the whole point was that we could now remove all of the possible particles that our electrons could hit, which meant that our electrons could now exist for long enough for us to see them, okay, or to come up with some observable evidence. And that evidence came into play with something known as the cathode ray tube. So what they ended up doing was pumping a bunch of electric current into one end of the tube, and at the other end you had your cathode or your anode, I forget which one's which, and the electric current would then flow from one end through the vacuum, and you could actually see a gas or a color associated with it. Okay? One of the more interesting things that happened out of this too is that they also noticed this weird kind of fluorescence at one end of it, and that if you exposed a piece of photographic paper at one end, the photographic paper started to change color as well, or change its appearance. Even when you wrapped the entire tube, okay, so that it was completely blocked off, you just wrapped it in, say, dark paper, and you put that photographic paper on the outside, even then it changed color, okay, which is an interesting phenomenon. We say nothing is passing through, and yet somehow or another, our photographic paper is responding to something. That discovery was the discovery of X-rays. Okay? And so the X-rays are a natural repercussion of the electrons hitting and exciting the surface of the glass. They release that energy with the form of X-rays, and then that X-ray can then pass through our dark cardboard layering on the outside, and that's what ended up hitting our photographic paper. So just by having a vacuum, we found a whole bunch of these interesting particles, which is kind of neat. He went through and theorized, once he's discovered that we have these particles that are electrons, that our atoms are now no longer completely indivisible, like what Dalton had, I shouldn't go backwards, like what Dalton had suggested. Dalton said all of our atoms are completely indivisible, that's it. Okay? Once we have a hydrogen, it's done. Okay? It doesn't get any smaller than that. Once we have a nitrogen, it doesn't get any smaller than that. Okay? Well, if we put in a vacuum and we've removed all particles, and yet we're still seeing some observation, something has to be passing through there. Okay? And that something happened to carry a charge. Okay? That's why we could see it pass from one of those electrodes to the other electrode. So he postulated that we've got these things called electrons. Okay? Well, if our atoms are made up of electrons, we also have an issue, because then every single atom would be negatively charged. Okay? So part of his counter theory then means we also have to have the countercharge within our atoms. So our atoms are made up now of these electrons and protons. And so then he said, okay, well, how do those electrons and protons exist within the atom? So his theory comes out as the plum pudding model. Okay? That's his theory. I know very little about the model and always have to remind myself about it because it's the wrong model. And so I consistently forget about it. His theory, if you've seen plum pudding, is this weird, nasty pudding mixture with these giant plums floating through it. Okay? And his theory was that the electrons represented the plums, and the rest of the pudding was this sea of positive charge. Okay? So the sum total, or the mass of our atom, is in the sum total of all of those individual particles, just kind of free floating around, with no real structure or order behind it. Okay? I always like to mention the Milliken experiment because I think it's kind of fun. It's not in your textbook, and you will potentially see questions on it, so you should pay attention. Milliken, Fletcher, eyesight, and patience were responsible for determining the exact charge of an electron. Okay? So Thompson gave us the relative charge, the charge to mass ratio, so that we know our electrons are negatively charged, but we don't know how negative they are. We don't have the scale on it. Milliken was able to go through and design an experiment that he then made Fletcher go through and perpetuate. Okay? So we've got a rough image of our diagram here of what that experiment was. So they took this nice little closed box, and they noticed that oil droplets have a charge associated with them, which means there has to be an imbalance of the electrons. So what they went through and did is then sprayed that oil, and you can then cause the oil droplets to move different directions depending on the electric field. Okay? But if you just sprayed a bunch of oil droplets, you've got probably hundreds of thousands of droplets, and that becomes very difficult to track any one droplet. So what they set up was this nice little experiment where they sprayed the oil droplets into a little container, and at the bottom of that container was a tiny hole. Okay? And eventually what's going to happen is one of those droplets will fall through that hole. While looking through the eyepiece, as soon as they see that droplet, they start playing with the electric current on the ends of that section. Okay? And what they can end up doing is, if they've got it timed right, they can cause the droplet to levitate. Okay? If our droplet is negatively charged, then what I can put at the bottom here is a negative charge. What happens when the two negative charges get near each other? They repel away from each other. So they can get that droplet to levitate, if you will, in between, depending on how much electric current they've passed into this. Okay? Well, things don't just levitate. Okay? What is it levitating against? Negative charge is causing it to levitate, but what's causing it to push down? Gravity is causing it to push down. Okay, so what they can go through and do is modulate that electric current. They can approximate the size of the droplet based on all the optical microscope properties. So once they've got the size of the droplet, they can predict its mass. They now know the downward force, because you can use gravity to determine the downward force of the droplet, on what force in that downward direction it has. To get it to levitate, what has to happen? We have to have an equal and opposite force going the other direction. They know everything they can about that because of the electric current that they are now modulating in, which then means they can calculate the charge on an individual electron or an individual droplet and use that to predict the actual charge on an electron. Okay? Well, there's all sorts of variables within that, which means the experiment more than likely failed a couple times. Okay? Or they only get one result and they got tons of error in it. How can we minimize that error? Do it again, and again, and again, and probably doing this thousands of times, calculating the results each of those thousands of times, and then averaging those results out. Okay? So you think our labs are tedious. This guy was literally sitting in front of a microscope and spinning a dial, hoping a droplet floated, and that the microscope optical qualities were enough that he could see the droplet even fall through. Okay? Extremely tedious experiment. Yeah?
Was it like an actual microscope, or was it just an eyepiece?
I don't know the details on that, in all honesty. Yeah. Something that would allow you to see the droplet so that you could predict something about its size. Because you need to know the size to be able to predict its mass and all that fun stuff. Okay? So at the end of that, they actually calculate the exact charge on the electron. We're looking at 1.5924 times 10 to the negative 19th coulombs. Guess what unit a coulomb represents? Charge. Okay? And officially, it represents a negative charge. Okay? So kind of a neat little experiment for them to go through and design. If you look up this kind of oil spray experiment, you'll only see one name attached to it. What's that one name? Milliken. Guess who did the experiment? Fletcher, who was probably the graduate student or postdoc student of Milliken. Milliken said, hey, go do this experiment. Fletcher then had to go out and do it, do all the work, probably even come up with all the results, and then took it to Milliken and said, hey, this is what I found. This is really cool. And Milliken said, yeah, you're right. This is really cool. I'm going to go publish it and stamp my name on it. Welcome to science. Okay? That said, Fletcher is now famous within the scientific community, and he could get whatever job he wanted because he now has a great recommendation from his advisor, Milliken. Okay? So kind of a crappy system that we've got set up, but it does sort of work. Okay? So that was a nice little step away for the moment, but we now think back to our Thompson model. We've got protons and or positive charge and negative charge just free floating completely within the atom. This is his first guess at a model. Okay, and one of the things that we like to do is then come up with some experiment to prove or disprove the model. All right. I have no idea on the truth on this aspect, so don't quote me on this. But I like to think that Thompson and Rutherford did not get along very well. Okay? Because Rutherford came along and designed an experiment to test Thompson's model. So what he was able to do is he was able to find a really high energy source of radiation of very pure quality, and we'll talk about that in a second. And he fired that high energy source at gold foil. Okay? Well, if Thompson's model is correct, just a sea of electrons and protons, there's no single point within that that has a substantial mass. Which means when I fire this radiation of alpha particles that has mass at that gold foil, what should happen to that particle? It should pass straight through. Remember, Thompson's model has no center of mass. It's a complete free-floating blob. If we fire a particle with mass, that's going to then go right through it because it can't impact anything. There's nothing solid to get in the way. This is why I like to think that Rutherford's experiment, or Rutherford didn't like him. Okay, why? If Rutherford actually believed Thompson's model, he would have changed his experiment a little bit. So what we're going to end up detecting on the other side of that is the radiation that passed through. So we set up a detector on the outside. Okay. If he wanted to prove Thompson's models correct, how big should his detector be?
A lot.
It should be very small. Okay. Just on the other end of the gold foil. Okay. Because what is that going to then show? All the radiation that passes through hits the detector. That means there's nothing of mass, of substantial mass, in the gold foil. What did Rutherford actually do with his detector? He made it huge, and not only huge, he made it going pretty much entirely around the gold foil. Why would he do that? If he trusted Thompson's model, say, well, the electron or the radiation should just go flying straight through. There's no reason to build a detector out here because that's just costing money. If nothing's going to impact that, why do I care? Okay, so we could say they didn't like each other, or Rutherford was just a good scientist and said, we need to test this as optimally as possible. Okay. So if Thompson's model is correct, we fire the beam through, hits the back end, we don't see anything else. Only that part of the detector recognizes stuff. They fired up the experiment, and what did they see? They saw that most of the particles did impact the back. Okay? Most of the time, that radiation passed directly through the gold foil without any kind of deviation from the path. Except every so often, you saw some particles scattering off, okay, at different angles. Okay? And even some of the time, you saw particles almost bouncing directly backwards. How could a particle with mass go backwards if it's being pushed forwards? It has to hit something of mass to force it to come back the other direction. What does that mean for the Thompson model? It's wrong. Okay? There is something of significant mass inside our atoms. Yes?
Does the Thompson just believe it was this, for lack of a better term, just a floating ball of energy in a way, or a charge?
Floating ball of charge.
Yeah.
Okay? And it ultimately is a neutral charge because within that floating ball you have positives and negatives. Okay? So it does neutralize out, but he's just saying we just have a floating ball of random charges associated within that with very little mass associated with it. Okay? Rutherford challenged that, and with this experiment, he could now say that, you know what, that doesn't work. What did he just prove the existence of? A nucleus. Okay? The additional information that goes on top of this, alpha particles carry a positive charge. Okay? What does that mean our nucleus must be? If it's negative, what happens is the electrons come up to it, or alpha particles come up to it. They'd be attracted to it, and they'd stick. They don't stick. What does that mean our nucleus must be? Positively charged. Nice try. Okay? So what does that mean? All of our positive charges are not this weird plum pudding, free-floating mass of positive charge. They're now all centrally located. Okay? Central is an odd term. On the average, it is centrally located. Okay? Which means when our alpha particles come up and impact, most of the time they pass straight through, because all of our protons are in a single spot, and our electrons don't have enough mass to cause any kind of bouncing effect. Okay? But every so often, that radiation comes through, and it directly impacts the nucleus, which then causes that reverse bounce back, and we now see the results out of Rutherford's experiment. Okay? Kind of a neat observation, isn't it? Well, to me it is. Okay? So, now the question becomes, where did you get this source of alpha particles? Anybody know what alpha particles are? Radiation, what type of radiation? Gamma rays are actually a byproduct of this type of radiation. It's not the same thing. What type of radiation is this? Nuclear radiation. It's nuclei decomposing. They got too big and they fell apart. In the process of that falling apart, they release some energy, or sometimes they release a particle, a physical particle. Alpha radiation is one of those things. If you move into Gen Chem 152, they talk about that type of radiation. Okay? But this whole experiment, and this is where we kind of move off on a slight segue here, sources, or is based on a clean and pure source of alpha radiation. If the alpha radiation is not clean or controllable, what happens? It goes everywhere, which means when I look at the results over here, if I can't trust my radiation source, I could have random stuff happening within the beam and causing all sorts of odd noise within my experiment. Okay? So we need a clean source of that alpha radiation. If it is not clean, the experiment fails. Okay? Why is that super important? Where do we get a clean source of radiation? Sun's an interesting idea. We don't get alpha particles from the sun.
From a pure element?
From a pure element, and in particular a pure radioactive element. So you guys picked uranium. Uranium is radioactive. But how readily available is pure uranium? Remember, we need to get it pure, because if it's not pure, we fail on our experiment. Okay. And if we think about our current crisis with Iran, it's not pure. They don't just go into the soil, dig out, oh, there's pure uranium, and now I move on. We have to purify it. That purification process is a very tedious process, and we need to know how to do it. If we don't know how to do it, Rutherford can't do this experiment. Okay? Current science is fascinating, because what happens when we find out how to do something? We slap a patent on it and say nobody can do it unless you pay me $1 million. Maybe it's $1 billion, whatever. Okay? You have to pay this ridiculously exorbitant fee to use my technology. Which means what happens to the likelihood of Rutherford's experiment? Not very likely to occur, because he can't obtain the pure radioactive sample. Okay? It's neat that this process actually happened in the past, because we weren't as patent happy then as we are now. Okay? Anybody tells you that patents produce more science is a load of crap. Okay? So where did that source come from? Who was that genius person that went through, determined how to purify a radioactive compound, and then said, you know what, I'm not going to patent this, I'm going to provide this to all of science so everybody has access to it and everybody can complete these experiments? Remember, we're talking 1900s. Odds are that person was male and white, unfortunately. Okay? We're just being honest with the situation. Okay? Who was it actually? Was white. French, damn it. And female. Okay? Early 1900s, you didn't even have the right to vote. Okay? Who was this miraculous person? Curie. Curie worked on, remember that previous slide where we saw this weird, our photographic paper all of a sudden changing colors even when we blocked out that box? They were like, wow, that's bizarre. Why is that happening? Curie was really interested in that. And so she worked with a variety of other people that were studying that phenomenon, known as X-rays. Okay? They tried to find other sources for X-rays. And in that process, they discovered radioactive elements that could also go through and do this. Okay? Can't vote, really have no rights, and yet she's somehow becoming one of the greatest scientists, both personally because she's actually releasing information for science, okay, and actually making these discoveries. Incredibly important person. Okay. I don't remember how much I actually say on that. Okay, so where do our alpha particles come from? It's a radioactive source, which comes down to Curie. The source that they use for your alpha particles, I always seem to forget this one, so I might be wrong. Radium. It was the purification of radium that Curie came up with that then released to the public that allowed Rutherford to go through and have a nice pure source. Radium is that critical discovery that allows Rutherford to move forward. Without that discovery, this experiment could potentially take tens or hundreds of more years. Okay? Because you need to find somebody else to come up with that process or wait for the patent to expire. Let's push the Curie thing even further. Okay? Why else is she a really cool lady? This was a pretty incredible discovery. Okay? Really, really important and advanced science relatively quickly at the beginning of the turn of the 1900s. Is it the 20th century? Turn of the 20th? Yeah. Turn of the 19th? Yeah. Whatever. One of those numbers. Okay. But she's a woman. So how much respect do you think she got? Not very much. In her own country, okay, every country has the National Academy of Sciences or some variation of that. The French Academy denied her. She was not allowed to be part of the group of scientists that are the brilliant minds of that country. Thank you, France. Okay. They have since gone back on that posthumously. You know, that's nice. Okay. But we also have a prize awarded, $1 million, right, for really important discoveries. What was that discovery? Or not what the discovery, what's the prize? The Nobel Prize. She won the Nobel Prize. Pretty cool. She got the Nobel Prize for her work on radioactivity. Okay. Guess what? She won the Nobel Prize twice. She is, regardless of sex, she is the only person to have won the Nobel Prize twice in a science field. Okay. Incredibly brilliant person. There's a second person, Pauling, anybody know? I think it's Pauling, could be wrong on that, that won a Nobel Prize in science and then won a Nobel Prize in peace, I think. So there's only one other person that has won 2 Nobel Prizes.
Is the Nobel Prize still I know last year someone got it for creating blue LEDs.
The creation of a blue LED is incredibly difficult to do.
Yes, but I
Yeah.
thought
Yeah. So
things that were done.
you may be jaded in the discovery and say, oh, that's really simple. A blue LED is actually incredibly difficult to do, and the science behind generating that is actually pretty impressive. So it is still respected, just because the results don't look as phenomenally cool. I mean, really, she got a Nobel Prize for purifying something. If you really want to call how cool is that, that's really not all that cool. She just purified something. Okay? You purify stuff in lab. Remember the sand, salts, and ammonium chloride lab? You purified each of those 3 species. You didn't get a Nobel Prize. Okay? So it's the level of the science behind it. Okay? The level of science behind a blue LED versus purification of radium is pretty important. Okay? And as far as its worth, there's plenty of science departments that's their selling point. We are the best chemistry department because we have 12 Nobel Prize winners. Okay? So it is still pretty high up there.
What was the other thing she was awarded?
I think she got 1 in physics and 1 in chemistry, and they both revolved around radioactivity, I believe. Okay. Other unfortunate thing, she studied radioactivity. What did she think of the hazards of radioactivity?
She died.
She didn't think anything was dangerous with radioactivity, and she ended up dying because of it, because to move your radioactive sample from one lab to the other, where'd she store it? In her pocket.
Oh, God.
Okay. That kind of causes problems with health. Okay.
Didn't 2 guy scientists like steal her work though? Like, wasn't she
You're
one of the-
thinking of DNA, I believe.
Did-
Yeah.
never mind.
And that's also a real fun one. We'll see how history looks on that one.
Did they not understand cancer in those days?
Nope. It's not a process that was, or the source of cancer.
It got discovered just only years later then, huh?
Remember, it's the source that's
Right,
important.
that's what I mean.
Even now, we don't have a clean source of cancer, because there's some people that we have clear reasons why, and there's some people we don't. Okay, so that's still an active research. So, impressive person. Remember that. Gave us the model of the atom. Let's get an idea of scale. An atom has a diameter of about 10 to the minus 8 centimeters. That's pretty small, but as we may remember from looking at chapter 2 and our PSS chapter, 10 to the minus 8, how small is that? Is that like that small, that small, that small?
Smaller than
Okay. We have really no way to conceptualize that size. Okay? Particularly if we then go through and say the nucleus is 10 to the minus 13. Okay? Well, it's just a minus 5 difference. I mean, that's not that big, right? Okay? It's pretty massive. So let's actually scale this up to something that we can look at. If an atom were the size of a superdome, okay, so we take a look at the superdome. I don't remember where it is. One of those big football stadiums. Okay? The nucleus is the size of a marble and in the middle of that. That's a pretty significant difference between the nucleus and the size of the atom. Okay? So we do have this big, massive difference in size here. That means all of our protons are centrally located, which brings up another interesting question. Rutherford also predicted the existence of a neutral particle in addition to protons. Why? Where were all our protons located? In the center. What happens when I bring the north end of a magnet near the north end of a magnet? They repel. So what happens when I take a positive proton near another positive proton? They repel. How can I get the existence of a nucleus with all this positive charge if all that positive charge is just going to repel away from each other? We need something to hold it together. That something can't have a charge, because if it's negative, then it's an electron. Okay? So what we have is this neutral species that we put into our nucleus to stabilize the existence of the nucleus. Whoa, that was not what I meant to do. Okay. It's that charge repulsion that we would expect for our proton that means we have something else there. That's our neutron. The neutron, who is it? James Chadwick. Not a big deal on the name there. Experimentally proven by James Chadwick. It's the size of a proton, and it has no charge. Okay, so the same mass as a proton, but no charge. So, in our summary, we've got our summary of subatomic particles at the bottom here. We've got electrons, protons, and neutrons. Okay, because we are ever lazy, we don't want to write out electron, proton, and neutron every single time we want to talk about them. So we come up with a symbol for them. The symbols we use: E for electron, because
Starts with E.
electron begins with E. Okay, P, proton, because it starts with P, right? N, neutron, because nucleus starts with N. No, neutron. Okay. You'll also notice that within our symbol, we've added some extra information. What is in the upper right-hand corner of each of those symbols?
Charge.
A charge. Okay. So if we go through and look at the relative charge, so remember Milliken came through and told us what the exact charge was. How many of you remembered that number? Actually, I should put my hand down. Really? What was the charge?
I wrote it down.
Oh, dang it. It was 9 point something, 10 to the...
1.5924 times 10 to the negative 19.
Okay, for those of you that wrote that down, you don't need to know that number. You can stop writing that number down.
Good.
Okay. What we care about is the relative charge. Okay. So the charge on an electron is the complete opposite of the charge on a proton. So if we just say the charge on an electron, that 9 point whatever number, if that's negative, then the charge on the proton is the positive version of that. So we just set it equal to 1, we kind of ignore it after that. Okay? That makes life a whole hell of a lot easier, so we stick with this -1, +1 when we're looking at our electrons and protons. The location of our electron, or the location of our proton, take your pick. Proton is in the nucleus. Well, if it's in the nucleus, where does the electron need to be? Outside the nucleus. Right? Last particle we could look at would be our neutrons. We needed the neutrons to stabilize the nucleus, to keep those positive charges actually glued to each other. Okay? So they have a 0 relative charge. So we could specify that with a 0 next to them in our symbols. Those charges are incredibly important to remember for each of the particles. We will constantly be referring back to these. The next part is the mass of each of these particles. It turns out that the mass of an electron is incredibly tiny. The mass of a proton is significantly larger. Okay? The exact mass is some weird super tiny amount, 9.612 times 10 to the minus 14 kilograms or something ridiculous like that. We don't want to have to remember that, so what we end up doing instead is setting up a definition. We say the mass of our proton is 1. Because neutrons are the same thing as a proton except not charged, the mass of our neutrons is also 1. Our electrons are, for all intents and purposes, just a charge. They carry very little mass. Their mass is 1/1836, the mass of a proton. Okay. What does that mean the mass of an electron is comparatively?
1836 of
You would say 1836 of the mass of a proton. That's a bit of a mouthful. Okay. So let's try this. What is my mass? This is a dangerous question, but it doesn't really matter. Pick a mass.
175.
175. That's very generous. Mass of my pen. What's that? Anybody?
2 ounces.
2 ounces. Now that I'm holding the pen, what is the mass of the pen and me? 175 plus 2 ounces. Why did you not include the 2 ounces in that 175 pounds? It's insignificant. What's the mass of an electron relative to a proton? Insignificant. What we end up saying our mass of an electron is, what is an insignificant number? 0. Okay? Makes things a little bit easier. All you got to remember are ones and zeros and negatives. Okay? Questions on that? Okay. Next part is taking a look at atomic notation. Your textbook refers to it as atomic notation. I don't like referencing it as atomic notation. It is more importantly referenced as nuclear notation. It is what does our nucleus look like. Okay? So when we look at our notation, we reference the atomic number and the mass number. Okay? The atomic number is given the symbol Z. I don't know why. The mass number is given the symbol A, because when you look at the word mass number, A shows up as the second letter, so that makes the most sense for the symbol for mass number, right? You're really going to accept that? Fine. Then that's the reason why it's A. Z does not show up in the word atomic number, so that's why we pick Z, because it's the letter that does not show up. Is that one also equally okay? Sure. Okay, fine. We'll just accept it. Atomic notation. So when we look at our atomic notation, first off, we need to know what element we're looking at. So we'll use our symbols, because we don't want to write out the name. So in this case, we're using SY to stand for symbol. Okay. In the upper left-hand corner, we will provide the mass number. The mass number is the sum of the protons and neutrons. What was the mass of a proton? 1. What's the mass of a neutron? 1. The number written in the upper left-hand corner should always be, can't be 1 because it's the sum of protons and neutrons. Greater than 1. Can it be 1.5? No, because it's the number of protons and the number of neutrons. Okay, so we'll always get whole numbers for that mass. In the lower left-hand corner, we will write the atomic number. The atomic number is the number of protons. Okay? So, it might be nice if we had a way to reference some of this information. Okay? So there's our symbol. An example. We've got that symbol written out for us. The element is?
Silicon.
Good. Let's see, did I step this? I did. Look at that. Silicon. The atomic number is 14. So it has 14 protons. That's all that information means. The mass number is 29. That is now the number of protons plus the number of neutrons. What is the number of neutrons? Holy crap, you guys did math really fast. We know that 29 must equal my protons plus neutrons. What does my protons equal? 14. What can I do? Subtract, and I'll solve for my number of neutrons, which should equal, if you guys did the math right, 15. Oh, look at that. You guys are pretty good. Okay? So it comes from knowing what those terms mean. If you don't know your mass number and your atomic number, and what they mean, you won't be able to figure out the number of neutrons. Okay? So you need to remember what those things correlate to and where you can find that information in our notation. I see a little question mark there. What's going on?
Oh, no, I was thinking.
No? Okay. So, next part would be a periodic table. Okay? It might be nice if we could reference this information on our periodic table instead of having to just be given to us. Okay, so we can use the periodic table to obtain a lot of this information. Okay? It gives us information about the atomic number, the symbol, and the atomic mass. So when we take a look at our periodic table, we've got carbon, usually specified in the center, and at the top, we provide the atomic number. Why is that weird? In our atomic notation, where's our atomic number? on the bottom. Sorry, it's the way it works. When we move to the periodic table, we put our atomic number on top. The atomic mass we put underneath it, usually. So if we take a look at our periodic tables on the left and right, if we looked at silicon, where's the 14? Sorry, our atomic number for silicon is 14, found in the upper right-hand corner. Nice that we're really consistent on where we place that number. The atomic mass? On the bottom, 28. Any questions? We look at the periodic table, we said the mass number was 29. Or sorry, at my problem here, we say it's 29, and yet you look at the periodic table and it says it's 28. That's a bit odd. Okay. Not only does it say it's 28, what does it say on the periodic table? It is 28.09. What did we say our mass number must always be? A whole number. Is it a whole number on our periodic table? No. What the F? Okay. This comes down to the structure of our atom. As we move up in our periodic table, we start to need increasing amounts of neutrons. Why do we need the neutron? To balance the proton. When we look at the mass of hydrogen, it is very, very close to 1. Why is it close to 1 for hydrogen?
There's only one proton.
There's only one proton. Do I need a neutron to stabilize the nucleus? Why do we use neutrons? To hold together the protons. If hydrogen only has one proton, do I need a neutron? No. Okay. So in hydrogen, I typically only have the proton. I don't worry about a neutron. What happens when I move up to helium? What happened to the mass? Okay. I have double the amount of protons. So I have 2 protons, and yet my mass is at 4. Why is it at 4? I need to add 2 neutrons to stabilize the counter-repulsion charge of those positive charges of our proton. Okay. As you continue to move through the periodic table, what you might start to note is a general trend. For every proton, there is a neutron. It's almost always a 1-to-1 ratio until you start getting way low in the periodic table. And now we end up having to add a whole bunch of neutrons, okay, in excess. Why? There's a lot of protons. We start running out of places to put the positive charge, so we have to fill in with neutrons to balance out that repulsive theory. So as we get bigger and bigger, we're now adding a lot more glue to hold our marbles together. Eventually, what happens? It destabilizes, and pieces start falling off of it, also known as radioactivity. Where are all our radioactive elements? The bottom of our periodic table with really high mass numbers and really high atomic numbers. Okay? So, atomic structure for carbon. How many electrons? Ooh, that one's tricky. We talk about how many electrons?
Yes.
How did I talk about how many electrons?
Said it's the same as proton.
Okay. It's typically the same as our protons if we have a neutral atom. Not necessarily stable, but a neutral atom. Why do we typically look for neutral atoms? Because they're lower in energy. Everything strives for a lower energy state, which is why we can get lights. Why? We're pumping electric current through. That's a very high charged species. It tries to stabilize by neutralizing itself within the gas, which emits light. Okay? Everything is striving for that lower neutrality. Okay? So if we're looking at an atom of carbon, we would predict that it will have the same number of electrons as it will protons. So how many protons does an atom of carbon have? How do you know it has 6?
Well, the mass is 12.01.
Its atomic number tells us the number of protons. The atomic mass is meaningless because the atomic mass is protons and neutrons. Well, at this stage, I don't know how many neutrons I have until I know how many protons I have. Okay? If I'm looking at a neutral atom, if I have 6 protons, that means I have 6 electrons. What happens when I move to the neutrons?
6.
In this case, do we get exactly 6?
No.
We get 6.01. Can I get, what is that, 100th of a neutron? No. So we run into this issue. Why is it not a whole number? Let's ignore that for the moment.
Inefficient.
It comes down to this phenomenon known as isotopes. Okay? An isotope is defined by the number of neutrons the element contains. Your protons will always define the element. If I have 6 protons, what element do I have? Carbon. If I have 44 protons, what element? That's a bit mean. If I have 22 protons, what element do I have? Titanium. 44? Ruthenium. Rubidium is Rb. Okay. You didn't have to know that. I was just curious. Okay. Neutrons define the isotope. Okay. That's going to change the mass. So our protons tell us what element we have. Neutrons tell us the mass of that element. And it turns out that I don't have to add 1 neutron per proton. We already talked about that when we get really low down in the periodic table. I can add more neutrons in, okay, to help stabilize that nucleus. When I'm all the way up at hydrogen, there's really no need to add a neutron. But can I? Yeah. And so what ends up happening is that we get different isotopes or different forms of our elements. Technically, hydrogen, as you guys were referencing it, is known as protium. Okay? And it is why we call it protium. What's in the nucleus? It's only a proton. We could also move to the species, another isotope of hydrogen, known as deuterium. You'll notice that what changed? Our mass number changed to 2. Deuce, sorry, is another reference to, be careful, 2. Our mass number is 2. Deuterium, because we have a mass of 2. What if I had a mass of 3? It's tritium, for tri for 3 for your mass number. Okay? So because I have these different isotopes, that's going to mess with my mass number. Because when I look at the periodic table, is that just hydrogen? Is that just manganese? No, it's all of the individual elements that make, or all the different isotopes that make that element. All the different atoms that have that many protons. Which means when I look at the periodic table, what I'm actually looking at for the mass is not our mass number, but the, not the mass number, but the average mass number. Okay? What would the average mass be for protium and deuterium? And don't cheat and look at the periodic table, because that's going to be misleading. Okay? If we take the average mass of those 2 particles, take the mass of protium, which is 1, plus the mass of deuterium, which is 2. There's 2 particles, so I divide by 2, and I get a mass of 1.5. So there's my average mass. So we say, hey, cool, everything's perfect. Check the periodic table. What is the mass number? Not 1.5. Why is it not 1.5?
It's a weighted average.
It's a weighted average. This calculation that we just ran is the same as saying 1 over 2 plus 2 over 2, okay, which is the same as saying 1 over 2 times the mass of the first particle plus 1 over 2 times the mass of the second particle. 1 over 2 is 0.5. This average assumes 50% of each of those particles. When we look at the percent difference between protium and deuterium, protium makes up something like 99% of the hydrogen isotopes. I need to change my calculation here to account for that 99%. Okay? So we're going to write that down here. How can I change my calculation to reflect that mass more appropriately? This was our percent protium. This was our percent deuterium. If I want to know my actual or my average mass, that says average, trust me, I need to know the percent of protium. Well, I just told you it was 99%, which means the deuterium is 1%. We now need to drop that into the calculation. It's not just going to be 99 times 1, right? I have to convert that across into the fraction. So I would get what for my calculation? 0.99 times the mass of that species, which is 1, plus 0.01 times the mass of the next species. What do I get for an answer? I haven't actually done this calculation. I just made up those numbers. I'm hoping it works. Is it 1.01? Seriously? Oh, awesome. Look at that. I'm a genius. Okay, so based on the dead silence, I got two questions here. Am I going too slow? So does that mean I'm going wickedly fast? Somewhere in the middle. Okay, so we got a mix in the crowd. It's okay. We've got our protons, neutrons, and electrons. Everybody's okay with those charges? Okay. Moving into the atomic mass, are you okay with the notation? Atomic mass, upper left corner, atomic number, lower left corner, symbol for the notation.
Yeah.
Remember, when you interpret off the periodic table, everything goes haywire, everything swaps around on you. There's an easy way that you don't have to remember it on the periodic table. All figures should have a key or a legend. Take a look at the bromine in the center of that table. What does it tell you the 35 is? The atomic number. So what you need to know is, what is the atomic number? The number of protons. Okay. You can then interpret off the periodic table. So if you remember your notation, you're fine. The next issue is then moving into this isotope effect and coming up with the masses out of it. Okay. I honestly do not have a better way of explaining that. Okay. That is the best method I can do for that. Some of you seem to have that nailed down. For those of you that don't, talk to me after class. We'll go through it again a little bit slower, and you can pinpoint and say, I don't understand why you did that. Does that make sense? Okay. And for those of you who think it's too slow, we'll go back to the quiz. Talk to me in lab today, and I'll show you. I'll direct you to it. So, we cleared it all because I can't write anything on that. So the first question was about scientists. What do we have? Thompson. How do you spell Thompson?
That's all. It's you.
I'm just going to say that's Thompson. I feel really bad for the guy. What did Thompson do? What's that? First model. Okay, how did he get the first model? Cathode ray tube, which proved the existence of... Right. So with the existence of an electron, he can come up with a model. So he theorized our first model, which was our plum pudding model. He's more important for the existence of an electron. Next scientist. Does not have to be sequential order. Curie. What did Curie do?
Provide a pure source.
Pure radioactivity. Next scientist.
Chadwick.
Chadwick. It's kind of funny that you all mentioned Chadwick because I think it's Let's not record that part. I don't remember his name at all. Actually, the only reason I remember his name is I've got a friend named Chadwick.
I can't name
Chadwick, what did Chadwick do?
Discovered neutrons.
He was the existence, so he gave the proof
Right.
of a neutron. Another scientist, Rutherford, gave us. We've got the existence of the nucleus, and a couple people also threw out another thing in here. Theorized neutrons. Because we have a nucleus of positive charge, said there's got to be something in there holding those positive charges near each other, so he said neutrons should exist. Chadwick proved it. Rutherford guessed. There's one more name, right? Or could make the argument of two more names. We have Milliken and Fletcher, which were... It's the oil experiment, so I would accept that, at least if it was a short answer.
Exact charge.
And it gave us the exact charge on an electron. That says charge, and that's an E. Okay. Any others that you remembered? I think that's all of them, isn't it? Okay. So, Thompson's up there. He's the top.
We need to know John Dalton.
Oh, Dalton. It's a good name to remember. Mainly it's his theories that you should be remembering on atomic interactions, I guess, if you will. So we had those 5 tenets of what made up chemistry. And of those 5, 3 of them were wrong. So it's remembering how he designed an atom. What was the second question? Honestly, I don't remember. What are we going to talk about next? That's a good answer.
That's what I wrote.
It's a good call. Why might I ask this question?
I just have a question real quick. You said
Okay.
that 3 of them were wrong. It says in here that 2 of them were incorrect. Which was something like that?
So let's pull up the slide here real quickly. It's going way back. Whoa. An element is composed of tiny, indivisible, indestructible particles called atoms. Is that correct? No, we have subatomic particles. So 1 is wrong. And this is where we're going to run into an issue with the book. All atoms of an element are identical and have the same properties. Why is that wrong? Isotopes. Whoops.
that. 3 of these.
More than one form. Those last 2 were right. Oh yeah, never mind. I thought there was another one in there. So yeah, it is only 2. 2 were wrong, 3 were right. So it's good that we pulled that up. This is why I don't have to take the test. That was kind of a joke. Come on. Number 2. Okay. Why might I care about what's supposed to be talked about next? Studying. You are supposed to be preparing ahead of lecture. Okay? If you aren't reading the textbook ahead of lecture, you are hearing what I'm talking about for the very first time. Odds are the very first time you hear it, you don't remember it, you fail at it, and you think I suck. At least one of those could be true. Okay? Ideally, you read it first so that when you come in, it makes a little bit more sense and you can start to work with it. Okay? So that's why that question's there. What was question 3?
When's the homework due?
When's the next homework due? Next Friday. Every 2 weeks. It's the even weeks of the semester. That's when the homework's due. Even if we got an exam, I don't care. You should have been working for the exam. Guess what that work was? Your homework. Just turn it in. Okay. Next question. 88 protons. So where do we put our 88 protons? No, we don't put our protons on top. Our mass number goes on top. Okay, what was our atomic number? Okay, now you're telling me different things. Okay, so I'm going to have to close out of that. Let's go to the quiz so I can see it.
That's radium.
Isolated with 88 protons, which is the atomic number, which is shown where? The lower left corner. 88 protons and 138 neutrons. What's the mass? We add 88 and 138, and we get 226. Okay. And the symbol would be Ra. Why would I ask a question about this? One word answer. Curie. That's why we talked about it. The most important discovery, right? Curie with purification of radium. Come back here. Okay. Last question. Why did I ask this one? It is not what we are talking about next. It's what I talked about over the weekend because you guys went through and watched the lecture because everybody got that question right on the exam where it said that you were going to go through and watch the lecture on nomenclature. It was a long video. I'm not going to lie. But there's a fun thing about long videos, and this still mind boggles me because everybody goes, oh, you can't have longer than a 5-minute video. Nobody watches it. Fine, I'll accept that. What you're saying by it's too long is that you don't know how to use a mouse. Because the mouse can roll over to the button that says pause, and you can click the button that says pause. It's now a 5-minute video. It's really not that difficult. Right? So you don't need however long the video is to watch it. All you got to do is you need 5 minutes, watch 5 minutes, pause, come back to it later. We've got that ability. Okay? It's an amazing thing, I know. Okay, formula for magnesium chloride. Okay. So what we would do is provide the symbols for these. We've got Mg and we have Cl. Okay. And this part, I will admit, the amount of material in that nomenclature video does rely on stuff we are now starting to talk about. What is the charge on magnesium? It is a +2 charge. If you don't know that yet, that's okay. You will be responsible for it, though, so start working on it. Charge for our chloride? -1. We said all things strive for neutrality. Would this compound be neutral? We take the charge of the magnesium, we add the charge of the chlorine, and we'd have a +1 charge. It is not neutral, so we must fix it. How do I fix it? So we could bust out a big long formula on that, and since you suggested that, it's not, stupid eraser. We could say the number of our element, X magnesium, times its charge, plus the number of the next element, times its charge, must equal, when we're naming, the overall charge, which has to be 0. This gets a bit tricky because we now have one equation and 2 unknowns. That is technically unsolvable directly. The indirect method, what do you mean by substitution? I agree. Yes. X and Y must be whole numbers. Pick a number that's easy to work with first and see if it worked. Let's say X is equal to 1. We get +2 minus Y equals 0. What does that mean? Y equals 2. What did I say Y was? Don't tell me 2. The number of chlorine. I need 2 chlorines. My formula becomes MgCl2. There's my answer. Okay. Last check is you have to make sure you use the smallest whole numbers possible. Officially, it's Mg1Cl2. Can I go any smaller with those numbers? No. There's my formula. The 1 can be implied. I can erase that, and should be implied, so we can erase that. Okay? Slow, methodical process. It comes down to rules and following those rules. There are shortcuts. I never recommend shortcuts. Okay? Once you've done enough practice, then you can build in shortcuts because you now know how to do it. You can start jumping circuits, which should have made sense. Okay. Next one, provide the name for S2O7. Okay. This one gets named differently from the previous one. Why? It's not ternary. Magnesium is a metal. Chloride is non-metal. There are rules for naming compounds that have a metal and a non-metal. Sulfur is non-metal. Oxygen is non-metal. Different rules. The rules are ionic compounds, metal and non-metal, or molecular or covalent compounds for your non-metal, non-metal. The molecular ones get really easy. The first symbol gets written out as its name. The second symbol gets written out almost as its name, but we change it to have an ID as in dog ending. We now also need to specify the amount of each of those. In the metal, non-metal one, we can specify the amount because we know the charge on each of those species. In the covalent compound, there is no such thing as charge, which means we have to come up with a different way to specify the number of them. How do I know there's 2 sulfurs in the name sulfur oxide? I use a prefix. That prefix is merely disulfur, specifying that there are 2. So it's a Greek prefix. How do I specify that there are 7 oxides? Hept. Okay, we could go heptaoxide, but then we've got the A and the O on top of each other. It typically simplifies out to heptoxide. You might see heptaoxide, kind of depends on the phrasing. Changing those names a lot of times is not obvious. You end up just kind of making whatever name sounds best. Why do you not need to stress too much about spelling these correctly? Not English, interesting call. True. It's a multiple choice exam. Okay? And I wouldn't test you on your spelling abilities if I can't spell properly. Okay?